In this lecture, I am going to discuss the topic retiming. So, like pipelining and parallel processing, it is also a transformation technique that can be used to optimize the performance of any DSP system. So, the formal definition of retiming is that it is a transformation used to change the location of delay elements in a circuit without affecting its input output characteristics. And retiming is used for various applications like reducing the clock period of the circuit, reducing number of registers in the circuit, and for logic synthesis. So logic synthesis is beyond the scope of this course, and the first two applications will be discussed in detail in this lecture. Two IIR filters are shown here, filter A and filter B. So starting with filter A, it can be mathematically described by the equation yn is equal to xn plus wn minus 1, where w is signal at this point, and wn is defined as a of yn minus 1 plus b of yn minus 2. So wn is a of, this is yn, so yn is delayed by one cycle and multiplied by a. So this term is a times y of n minus a, and this at this point yn is delayed by two cycles and multiplied by b. So wn is sum of a into yn minus 1 plus b into yn minus 2. Substituting this yn to this equation, the final equation is yn is a of yn minus 2 plus b y of n minus e plus xn. So this is the mathematical representation of filter A. For filter B, let's say that W1 n is the signal at this multiplier and W2 n is signal at this multiplier. So W1 n is given by a of yn minus 1. So W1 n is yn delayed by one cycle and multiplied by a, and W2 is yn delayed by two cycles and multiplied by b. So W2n is b y n minus 2. Yn is given by W1n minus 1 plus W2n minus 1 plus xn. So yn is given by xn at this point W1n minus 1, and second signal is W2n minus 1. W1n and W2n will be delayed by one cycle, and at this point they will get added. Okay, so yn is x of n plus W1n minus 1 plus W2n minus 1. Substituting the value of W1n and W2n to this equation, the final equation is yn a of yn minus 2 plus b of yn minus 3 plus x of n. And so here you can see that yn is equal to a of yn minus 2 plus b of yn minus 3 plus x of n. So the equation is same. This means that these two filters are two different versions of same representation. Okay, so filter A and B have delays at different location, but input output characteristics is same. So here you can see that the location of delays are not same. Other topology is same, like the connections, input edge of a node, outgoing edge of that particular node. Only the change is in delay element, location of delay elements. So the question is how this different version can be derived from this one, from this to this or this to this. So the answer is retiming. So now comparing the characteristics of filter A with filter B. So number of delay element in filter A is 4 and in filter B is 5. Number of delay element is, total delay element in this is 4 and in this is 5. Critical path time for filter A is 3 unit time and for filter B is 2 unit time. So the critical path in this filter is this one, and in bracket the computation time of the elements are written. So it is 2, it is 1, so 2 plus 1 is 3, and in filter B the critical path is this one. So both are adder and critical path time will be 2. So critical path time is 2. Iteration bound for filter A is 2 and filter B is 2. So iteration bound can be calculated by using calculating loop bounds for every loop present in the graph and then selecting the maximum value. So a loop in this graph is this one, adder, multiplier and adder. So the sum of computation time of this elements are 1 plus 2 plus 1, that is 4, and number of delay element is 2. So loop bound for this loop is 2. Okay, calculating the loop bound for the same loop in graph P. The sum of computation time is same, that is 4, and number of delay element is 2, that is 2. Okay, so comparing these two loops, these two identical loops. Okay, so in this loop the delay element was present at this point, and in this loop the delay element was present at this point. Okay, but in the particular loop the total number of delay element was same. In this loop the total delays are 2 and in this loop the total delays are 2. Okay, so this is second loop, adder, multiplier, adder and then adder. Okay, so summation of computation time of these elements is 1 plus 2 plus 1, that is 4, and total delay is 2 plus 1, that is 3, 4 by 3. And for the same loop total number of delays is 2 plus 1, that is 3. So computation time, so the sum of computation time will remain the same, that is 4, and total number of delays is 3. Okay, so you can notice that the position of delay elements are not same, the total delays are same. In this loop the total delay is 3 and in this loop total delays are also 3. Okay, so iteration bound is not changed, and we can conclude that iteration bound is not changed as number of delays in a cycle in the graph is not changed, and number of delays element and critical path time can change. So number of delays are different and critical path time is different, but iteration bound is same, and total number of delays in a cycle is also same. So to transform the filter A to filter B, the technique used is called retiming, and it can be obtained by performing cut set retiming. Okay, so during pipelining I have already explained the concept of cut set. So cut set are set of edges in a graph in which the signal flows in the same direction, and if you remove the set of edges from the graph will become disjoint. Okay, so in this graph, now I have converted the filter A into its equivalent DFG form. So I will call it as unretimed DFG, and this is one of the possible cut set. Okay, so edges in the cut set is from node 2 to 1, 3 to 2, and 1 to 4. So if I remove these edges, the graph will become disjoint. So let's say that this subgraph is G1 and this is subgraph G2. So G1 and G2 are two disjoint subgraph. Okay, and the dotted line in red color is showing the edges that we have removed. Okay, so the edge from 2 to 1 is basically from G2 to G1. 2 to 1 is connecting G2 to G1, and edges from 3 to 2 and 1 to 4 is connecting G1 to G2. So 3 to 2 and 1 to 4 is connecting G1 to G2. So retiming is done by removing k delays from each edge from G2 to G1. Okay, so G2 to G1, the edge is 2 to 1. So you have to remove k delay from this edge. Okay, so there is only one edge that is connecting G2 to G1, so you have to remove k delay element from this edge, and you have to add the k delay elements to each edge from G1 to G2. So 3 to 2 is connecting G1 to G2, and 1 to 4 is connecting G1 to G2. So you have to add the k delay elements to these edge that is connecting G1 to G2. So let's say that k is 1. So this means that you have to remove one delay element from each edge from G2 to G1, and you have to add one delay element to each edge from G1 to G2. Okay, so G2 to G1 is connected by edge between 2 to 1, and there is only one delay element present. Okay, that's why I have taken k equal to 1. You can remove at most one delay element. Okay, so removing this delay element, and edge from 1 to edge between 1 to 4 and 3 to 2 is connecting G1 to G2. So you have to add one delay element to this edge and one delay element to this edge. Okay, so one delay element is added to this edge and one delay element is added to this edge. So the at this point the total delay element is 2 plus 1, that is 3. Okay, so this is the retimed version of this graph. Okay, you can verify it by writing mathematical equation for this graph and comparing it with mathematical equation of this graph. Okay. So other cut set can also be chosen. So in the same graph, this is second cut set, 2 to 1, 3 to 2, and 4 to 2. Okay, and if I remove these edges from this graph, it will be divided into two graphs, G1 and G2, two disjoint subgraph. Okay, so G2 is having only one node, that is 2, and G1 is having three nodes, 1, 3, and 4. So H from 3 to 2 and 4 to 2 is connecting G1 to G2, and H from 2 to 1 is connecting G2 to G1. Okay, so you have to do the same thing. You have to remove k delay element from each edge from G2 to G1. So You have to remove k delay element from this edge, 2 to 1, and then you have to add k delay elements to this edge, that is 3 to 2 and 4 to 2. Okay, so 2 to 1, 2 to 1, it is having one delay element. Okay, so again performing cut set retiming for k equal to 1. So remove this one delay element from this edge, so this delay element is removed, and add one delay element to edge between 3 to 2 and 4 to 2. So 3 to 2, one delay element is added, and 4 to 2, one delay element is added. Okay, so this graph is similar to the filter B that we have initially taken. Okay, so we have three versions of a same DSP system. This is version 1, this is version 2, and this is the third version. Okay, so you can calculate critical path time, iteration bound, number of registers, and you can have a comparison. Okay, so this is the one way of retiming a graph, that is a cut set retiming.